So in the last video, we talked about this idea of energy sort of flowing back and forth between, say, being stored in the motion of a mass and as kinetic energy, and then in the interactions within a spring as potential energy. And so we sort of drew this diagram where we said, okay, we have the kinetic energy of the mass, we have the potential energy that's stored in the spring, and there's some flow between the kinetic energy and the potential energy. But we didn't really talk about how it is that that flow happens. So how do we actually think about energy being transformed from one form to another, or energy flowing from a sort of kinetic energy storage location to a potential energy storage location, or from one kinetic energy location to another kinetic energy location? And so when we talk about the flow of energy, or energy transfer, there are a couple of mechanisms that we can use for that, but the one that you tend to see the most of when you're talking about mechanical systems is energy transfer through work, right? So work is actually is defined as the change in energy that, or by doing work, one changes the energy in a system, or one transfers energy from one system to another. I'll note it's a little bit different from, we talked about previously force being the flow of momentum. Work is not really the flow of energy in the same sense that force is the flow of momentum. And in fact, you would actually say that power is the analog of force. Power is really the flow of energy. But in order to get to power, we really need to talk about work first. So work actually is defined as the amount of energy that's being transferred due to sort of macro scale mechanical interactions. Okay. All of which is a very long-winded way of saying something that you've probably already seen in a physics class before, which is that the amount of work that a force does, so the work done by an interaction, is the integral of that force dotted with the distance or the path that that force is applied through. Okay? So this is what is called a path integral. So you're used to sort of the idea of work as force times distance. This is a generalization of the idea that work is force times distance. And what I want to do in a couple of the next videos is sort of talk about how we think about this. So we're first going to think about this in the really simplest case of a sort of one-dimensional situation. So let's think about the 1D situation. And I'll think about this sort of 1D situation where there's a box that's on the ground, it's some mass, there's a gravitational force acting on the box, it's a normal force acting on the box. I am pushing on the box with my very long arm, and so I'm applying a force to the box in that direction, and there's friction acting on the ground, so there's a frictional force acting in the other direction. Okay, and let's say I move the box from point A to point B. Right? With that framing, I could ask the question, what's the work that each of these interactions does? Right? So if I think about the work that's done by me, right? The work that's done by me would be the integral from point A to point B of the force that I apply, so F me, which I'll say is F me in the I hat direction, dotted with the path that I'm following. With the path that I'm following, if I actually think about a little chunk of this and say this is a distance dx, my little bit of the path is actually dx in the I hat direction, right? Because my path to go from A to B is just along this line. So pretty clearly I hat dot I hat is 1. Force of me times dx will just be force of me times, if I say there's some distance L here between these two, force of me times L, assuming that I apply a constant force. By the same token, the work that's done by friction would be the integral from point A to point B of the frictional force. Well, the frictional force is actually minus F in the I hat direction dot dx I hat. And so that work that's done is actually negative F times L. So from a sort of stock and flow perspective, we would say I am pouring energy into this thing. I am doing work. I am adding energy to the mass. And friction is actually sucking energy out of the system because of the fact that the amount of work that's being done by friction is actually negative on this mass, or equivalent, you could say the mass is doing positive work on the ground, if that were the way you wanted to think about it. But since we're assuming that this mass is our system boundary, this work is energy flowing into the system. This negative work is energy flowing out of the system. I, of course, could also ask the question, how much work is done by the normal force here? And again, I'd take the integral of the normal force times j hat dotted with dx I hat from a to b. Well, j hat dot I hat is 0, so this is pretty clearly 0, and by the same token, the gravitational force does no work. Okay, so this sort of idea is that work is actually this transfer of energy due to interactions, right? So it's actually a force that does the work, but the only way that the force actually does the work is by applying that work over some distance where the force is actually in some way parallel with the displacement that you're moving the object through.